All right. You may log in. You may log in now. And I sent you a document. Excuse me. I sent you a document called Area. Mercy.
Oh wait, mine won't let me.
All right. Should be able to log in. You should get a document called Area, which we will deal with here in a little bit. Okay, so just set that aside for right now. Now, let's talk about the homework. Get your homework out. And, oh wait, I think I said that earlier. And let's talk about what questions you had. Now, there's a couple of things I wanted to make sure we were very clear on. The main emphasis of yesterday was this idea of over and under approximating things. And so I want to make sure that we understand when I say that, what are we talking about? So if you have a curve like this, when I talk about L or lefts being under, that's what we mean. I mean, the area in the left rectangle is less than the area under the curve, right? And the trapezoid in this case would also be under, because a trapezoid would look like that, okay, on this particular problem. And then of course midpoints and trapezoids are always reverses of one another. Now, and we talked about concavity, so if it's concave down, a trapezoid is under. If it's concave down like this, a midpoint would be over. We talked about because a midpoint would actually touch along here, but we would pivot it. We showed that picture of pivoting the midpoint rectangle and turning it into a trapezoid that's actually tangent to the curve. And so a midpoint rectangle would actually be that trapezoid, that tangent trapezoid that's above. But understand that trapezoids and midpoints are opposite. If one's under, the other's over. And that includes if you get a curve that changes concavity, right? If you get a curve that changes concavity and you do midpoints to it, well, some of the midpoints will be over, some of the midpoints will be under. But overall, compared to trapezoid, it'll be reversed. And so your midpoint approximation, even if you do 20 midpoints on that curve, some of the midpoints will be over, some will be under, but when you add them all together, the approximation is either going to be over or it's going to be under. It's going to be one or the other, okay? And the trapezoids will be in reverse. Some of the trapezoids will be over, some will be under. When you add them all together, it'll be the opposite of whatever midpoint is. So if you get a midpoint approximation that is 0.137, and you get a trapezoid approximation that's 0.182, then what do you know about the actual area? Somewhere in between. You know that the midpoints are under because it's littler than the trapezoid, right? And you know those two kind of go together, right? But if I gave you 10 lefts and told you that that was let's say I didn't give you this trapezoid one. If I gave you 10 lefts and told you that that was 0.832, and I gave you 10 midpoints and told you it was 0.137, can you tell me anything about the exact area? Not really. Is it going to be in between the two? See, I don't think we know that it's going to be in between the two, right? Because if that's all I tell you is that 10 lefts is this and 10 midpoints is this, I don't tell you if it's concave up or concave down or increase or decrease. If you don't know any of that, or maybe it's all those things. Maybe it's a curve that does all that. It increases and decreases and is concave up and is concave down. If it's all those things, then I don't know. I mean, looking at the two, I might be tempted to say this one's too much. But do we know this one's over or under? No, we don't. So this one could be over and this one could be over. And so the actual area might be, 0.12, 0.11, right? So midpoint and trapezoid go together. If one's over, the other's under, and vice versa. And lefts and rights go together. If one's under, the other's over, and vice versa, okay? So keep that in mind. All right, and then we also learned yesterday that a trapezoid is a combination of a left and a right. That's why we can average the two, is because one's over, one's under, we average them, we get a trapezoid. And Simpson, likewise, is this, oops, that was a 2 in. So Simpson was a kind of an average of midpoint trapezoid, right? Again, because midpoint one is over, and midpoint trapezoid one's over, one's under, so we do this kind of an average, a weighted average, and we get this thing called Simpson. All right, so that's a little bit of a summary of yesterday. So, what questions do you have? We got to make sure we're clear on the notation and those kind of things. Maybe we can check a few answers if you want to do that on the homework. So, shoot, Steve.
Number 51, it said use some sort of rule. I forget what it was, but I don't think we did that.
Okay, well, right. Now I'm going to give you my sarcastic, smart aleck answer here. It is true, I did not use the term divide and conquer strategy or trapping yesterday. However, if you turn back 2 pages, this is a lost art in math class, and I blame myself mostly. Well, right now I'm going to blame you, but I haven't forced you to do that. So no more do we, if we don't understand a homework assignment, or a homework question, do we turn back in the section and look for it and read, right? We just assume, hey, we didn't teach us that. So anyway, yeah, it's the lost art of looking back in the section. So if you turn back 2 pages to example 6 on page 378, it does have an example where it talks about divide and conquer. So there you go, Steve. Way to go. Good job of asking a question and having me humiliate you. But, so no, you're right, and I expected we would have that question. I do want to spend some time talking about that one. Okay, this whole thing of divide and conquer. Now, example 6 talks about divide and conquer using left and rights. Number 51 asks about using divide and conquer using midpoint trapezoids. Right? So I tell you what, let's hold up because I want to get into some depth in that one anyway. So let's hold off on that one for the end. Okay? So what else? What else? What does this mean right here? If I write this right here, that's the exact area minus the approximate area, so that's amount of error, right? This is the amount of error. Computational error, approximation error, whatever you want to call it, but it's the amount of error that 10 left rectangles has. Or your book says commits, like committed an error, right? The 10 left rectangles commit a certain amount of error, okay? How much are they off? That's what that is, okay? So we see how we're going to see that here in a minute. All right, well, what I would like to, if there aren't any other questions, I would like to go through the answers to 29 through 34 real quick, because in the other class that ended up generating some questions. And so we'll see how you guys did. So on 29, you had what? Must be true, may be true, or can't be true. Must be true. Number 30. May. Why? Depends on concavity. Midpoints. All they told us is this function is increasing and it's positive, which means it's above the x-axis. So all we know is that this function is increasing. So we could have a function here that is doing this, or it could be doing this, or it could be just a straight line too, right? But we know it's increasing. That's all we know about. All right? So midpoints could be over. Which one of these would it be over? A midpoint. This one. Right? Midpoint is when you tilt it or pivot it and it would be tangent. So it would be above when it's concave down. Right? Probably the easiest way to think of it is a trapezoid. To be honest, when I think of one like this, I look at it and say, well, there would be a trapezoid right there. Midpoint's opposite. So a trapezoid's under, so a midpoint's under. Okay? All right, 31. Must be true. 32. Thirty-two is must. We'll come back to it. What's 33? Must. Now, if you looked in the back, 33 said may. Back is wrong. 33 is must. Let's talk about 32 and 33. Okay? 32 says that lefts, and Steve mentioned it, so I'll let him explain. Here's 32, right?
Right.
Is the left less than the midpoint? Okay, go ahead.
The left and the midpoint are both going to be, what, under in this situation? Right, or over?
Well, didn't we just say that a midpoint would be over on this one, but a midpoint would be under, right? Because this is a midpoint rectangle, right? Everybody's with me on the thing we did yesterday where we pivoted that thing, right? This would be a midpoint rectangle. So it's under on this one and it's over on this one.
Right. Well, the way I thought of it at least was, I thought they were both on the same, like, side, which they aren't. That
Okay.
basically L has a higher percentage of error, which means that it's gonna be more extreme in either direction. So I just thought if it had a higher percentage of error, it would have to be less than the midpoint.
Okay, I'm going to avoid the term percentage of error because that gets into some other technicalities, but amount of error, we're going to deal more in amount of error. Left and rights are going to have more error than midpoints and trapezoids.
Because the midpoint's the average of the left and the right.
No,
Well, like not the average.
trapezoid is an average of the
Yeah,
left
but I
and
mean
the right.
like the midpoint is the one. Yeah, the trapezoid would be, and then the midpoint is pretty much the same thing.
It's kind of, I mean, it's very similar to that. It's got a little bit over, a little bit under.
Can I go up there and show? Because it's easier for me to just kind of show instead
Go
of
for it.
talking.
So while
'Cause
he's,
how you
yeah,
said,
go ahead, go ahead.
how you said, oh, like this is either one. These are midpoints, right?
Right.
So it's gonna be right there. So you can think either the regular rectangle, and then if it's a left point, it's gonna be starting down here. Wouldn't it?
Right.
So then, and also same with over here, it's still gonna be lower. So there's still that little bit of area that the midpoint has extra.
So, yeah, I think you're all saying the same thing. I think what Steve is saying is talking about amount of error. Here's the amount that the midpoint's going to be off. Here's the amount that the left's going to be off. Right? The left's going to be off more. I think you're saying the same thing. I mean, you're talking about how they're an average. So the bottom line is, if a left and a mid. So let's go back to this. So the only thing Steve was missing in what he said is he was assuming that if left was under, the midpoint was under, and that's not quite true. But so let's look at both scenarios. Let's look at this scenario where the midpoint is under, and the left is definitely under. Right? We already decided that left is definitely under. So we got left and midpoint that are both under. Which one's under more? The left, right? Which means it's littler, right? So in that case, this is definitely true. What if the midpoint is over? Well, then it's for sure true, right? Because if the left is under and the midpoint is over, as far as an approximation, then the left is definitely littler. So in both cases, the left is little, right? And I'm sure what you guys were thinking when you thought may is you thought, well, hey, it could be this case where the left is under and the midpoint are both under. They're both under, so we can't tell which one's little, right? And I'm guessing that was your thinking. They both might be under. That's true, they both might be under, but the left is going to be a lot more under than the midpoint. Okay, and that's the same line of reasoning on 33. It's got left and trapezoid. Same line of reasoning. Here a trapezoid's going to be over, so a left will definitely be below that. And here a trapezoid's below, but not nearly as much as a left will be below. So it's got to be must. What do you have for 34 now? Maybe true. And that's this example right here. It's concavity, trapezoid and midpoint. We don't know what the concavity is on this problem, so we can't tell the trapezoid and midpoint. One's going to be over and one's going to be under, but we don't know which it is. Okay, so let's talk about 51. It sounds like we're ready to go. So get your calculators out. And that document that I sent you, you can go ahead and open that. Now, when I sent it to you, it should have put it in the MyLib folder. So if you go to your home screen, now you might have opened it up, but if you go to My Documents, it should be in, now your My Documents looks a little different than mine. All right. It must be, the MyLib must be inside of My Documents. There you go. So the MyLib folder is inside of your Documents folder, and there should be and this program called Area should be there. So I only show you that so in case you close it out, okay, in case you try up your calculator or whatever and it's not there, you go to look for it. The Area document that you need. I'll keep calling it, you'll hear me call it the Area program. And on our old calculators, it was a program. Actually, it's a document with programs in it. The programs that I didn't write, but I stole. Didn't steal, they were free. But I mean, I downloaded, you know, whatever. And then I made a few adjustments to one that I couldn't figure out how to, another adjustment I want to make the other one, but I haven't figured that out. Or I haven't spent time looking at it. But anyway, so it's really a document. Should be the terminology on these new calculators, but if you hear me say Area program, that's what I'm talking about. So you open that up, okay? So go back to that document. You can go back to your home screen and current document or whatever. But get your Area document up and go over to page 1.2. Okay, so we're going to make somebody be a presenter here. And thank you very much, Steve. All right, and so you should have this. You should have this page right here, and RAM stands for Riemann approximation method. Riemann approximation method. Now, on your particular calculator, all right, we're going to have there's two routes we can go, and that you can use for this. Now, when I told you yesterday that your homework for today was mostly no calculator. Some of you took that more literally. Well, like, why wouldn't you? I said no calculator. That user didn't use your calculator. But on some of those problems, you could have used your calculator to graph. You could have used your calculator to add up stuff if you needed to. If you're adding up 4 lefts. Okay, remember the rule going forward. If it's single-digit subdivisions, if it's L9, L10, L8, whatever, you write it out. Now, you can still use your calculator to add those up and all that stuff. Okay, you can still use it for that. But if it's 10 or more subdivisions, double-digit or more subdivisions, we're going to use our calculator to just give us the answer. If I ask for an L50, automatic permission to go to this calculator document I sent you and just have it do 50 lefts for you. You don't have to write anything out. So double-digit or more subdivisions, automatic permission to use this Area document. Okay, below that, single-digit subdivisions, we write it out. Okay, all right. So one option is to do this thing called RAM, Riemann approximation method. Now, one thing I don't like about it is it doesn't do trapezoids. Riemann, of course, is just rectangles. Well, it turns out it does Simpson's rule, though, and Simpson's rule is not rectangles either. So, you know, and this is probably something I should adjust in the program if I can figure out how to do it. But because the programming aspect of this calculator is a lot different than our old calculator we had. All right, so here's what we're going to do. We're going to go ahead on your calculator and hit enter right now. Okay, it says RAM, parentheses, which you can simply call up at any time by just typing in RAM. All right, and this little screen pops up. Welcome to the Riemann sum approximation program. You'll get left, right, midpoint, and Simpson's rule, and the definite interval. Now, there's several things I don't like about this one, and that is it doesn't give it to you the trapezoids, and it only gives you 3 decimal places, which sometimes we like to see more. All right, so go ahead and hit OK. Press enter to hit OK. And it comes up and asks what function you want to put in. Okay, so now, for the problem we're going to do, for number 51, all right, what was the integral? It was what, 0 to 2?
Sin x.
All right, now we purposely picked sine x squared because this is not one we can do an antiderivative on. So we really have no way of knowing the exact area here. Okay? Now I say that, one of the things that we are going to be doing over the next number of days is investigating this idea of how in the world does our calculator give us this answer. You know, because let's face it, we can't do fundamental theorem part 2 on this. But Steve and anybody else who wants to, go on your calculator and go to your scratch pad. Just come over here and hit your scratch pad right now. You should be able to do that. Does your scratch pad come up? It's because we're out of that. Okay, click cancel. Go ahead, everybody, just click cancel. Yeah, you have to keep clicking cancel. That's fine. Hit OK, but whatever. Don't worry about what you just saw. Okay, now look. Now listen. Where you were. Okay, go ahead and go to your template here. So now we're on the scratch pad. Now that's different than being in the area document. That's an important distinction that we got to pay careful attention to today. Okay. Stay with us, Joe. All right. So you go in here and you grab your template, okay, and you grab your integral thing right here, and let's do that integral. Let's go. Grab that integral. Okay. We're going to go 0 to 2. We're going to go sine of x squared. Now, while you're doing this, you know, when we typed in like x squared dx, and from 0 to pi or whatever, and we'd get 1/3 pi cubed or whatever, give us an exact answer, what do you suppose the calculator was doing? Antiderivative, right? It was finding an exact answer. Now, in this one, go ahead and hit enter. And look what it gives us. It doesn't give us an exact answer, right? It gives us a decimal. Why do you suppose that is? It's an approximation. The calculator is doing an approximation. Now, what approximation? Is it doing trapezoids? Is it doing midpoints? Is it doing Simpson? And if it's doing Simpson, how many is it doing? 100? Well, no, it is the matter because you can't do an infinite. It would never be done. You know, I mean, you're right. We talked about how the exact area we do an infinite number of rectangles or whatever, but the calculator can't do an infinite number. It's got to do a certain number, right? So what's it do? Does it do 1,000? Is that enough? Does it do 100? I mean, yeah.
Does it even matter how many with the Simpsons? Because
sure, because if you do S6,
because since we did the whole T3 and M3, and then it made the S6, it still got the exact answer.
well, that was only because it was a parabola. It was only a quadratic equation. Simpson fits a quadratic equation perfectly. Okay, for example. Getting a little bit, since you brought it up, getting a little bit into some stuff we'll talk about tomorrow. But if I gave you this graph right here, straight line, and did a trapezoid on that, it'd work perfect, wouldn't it? It'd work perfect. And midpoint would work perfect, right? And what if I gave you a graph like this and wanted to do area and told you to do 6 lefts? You get what I'm saying? It works perfect. So for certain graphs, certain of these work perfect, okay? And Simpson on a parabola works perfect, okay? And that's the only reason that one worked perfect the other day, okay? Normally it would not for most functions. So for this function, it would not work perfect. So if we did 6, so if the calculator was doing 6, okay. So if the calculator, you know, so what's it programmed to do? Is it programmed to do 6? Well, probably not. If it only did 6, how accurate do you think this would be? Not very. Probably if it did 100, more accurate. 1,000, more accurate. Now, it gave us like 13 decimal places here. I'm assuming that's accurate. I mean, you know, we want to trust the calculator. We put this in. I'm assuming that's accurate to 13 decimal places. So the calculator knows, hey, I'm going to give them 13 decimal places. I need to be accurate to 13 decimal places. So how many do I need to know? So that's in the program. So one time when you do an integral, it might do 100. The next time you do an integral, it might only need 20. The next time you do an integral, it might need 1,000. You see what I'm saying? Now, how's the calculator know? Well, that's what we're going to investigate over the next couple of days. And how in the world can the calculator know if we don't know the exact answer? Isn't that kind of an interesting question? If we can't do fundamental theorem part 2, which means we can't get the exact answer, then how in the world can we know when we're within 5 decimal places? How can we know when we're within 8 decimal places accuracy? How can we know? And so that's something we're going to be looking at over the next couple of days. Okay, but before we get to that, we've got to talk about error. We've got to talk about how, you know, how much is it off and when is it over and when is it under. That's why we're having these discussions. Okay, this is not a big part of the AP test, quite honestly, on the final or in our package. Okay, but I think it's really interesting when we're using these calculators to find these integrals and stuff to talk about how it's approximating when it can't find the exact area. How's it doing? Okay, so I think it's a worthwhile thing to do. All right, so everybody go back to your document. So I'm not sure what's the fastest way to go back to that. How'd you do this? Hit escape. Great. Okay. Hit escape, and we're back in. Now, this is important because being in the scratch pad is different than being in the document. We got to be careful of that. Now, notice in the document, where you'll do almost all your work in the document is in this 1.2 page. All this is a calculator page, right? Steve, type 2 plus 3 right now and hit it. Okay, this is just a calculator page like you normally do in your scratch pad. Okay, but we're in the area program right now. So you want to do any calculating here, you can do it. Okay, you can go up and delete things and so forth. Okay, so on this one, so let's go ahead and, all right, what we're trying to do here is we're trying to use the divide and conquer strategy using midpoints. Let's do 6. Let's do 6 midpoints and 6 trapezoids. I just pulled that out of here. Okay, now we're not going to write them out though. Okay, but 6 midpoints, 6 trapezoids, and they want us to use a divide and conquer strategy. All right, so let's go again back to your scratch pad, and let's graph this thing. Let's get a sense of the graph of this thing. So we're back to the scratch pad, onto the graph screen. Let's do sine of x squared. Now you guys don't, everybody doesn't have to do this part. Okay, so we're going to graph this. Now we want to go from 0 to 2, and this is good review for a lot of things we have to do when we get to the our packets and stuff. Yeah, let's go to our window. Let's just look from 0 to 2. Remember what zoom I told you to use here? When you know you want to go from 0 to 2? No, zoom fit. Zoom fit. Yes, see, I told you this was good review. So go 0 to 2. Oh. No, yeah, you first have to do 0 to 2. This is why zoom fit's so good with integrals, because we usually have a set region we're looking at. In this case, 0 to 2. So hit OK. Yeah, keep everything else the same. Because zoom fit's going to do the y's for us. So we go hit OK. And now we go to zoom fit. What zoom fit does is say, okay, you want to look from 0 to 2? I'll figure out what the y window should be for you. So it does that for you. So zoom fit's really good when you know your domain. So okay, we want to go 0 to 2. Now, here's the divide and conquer strategy. Now we're going to do way more than what you were expected to do on 51. 51 just said explain how we can do it. Now what we're trying to do is trap the interval. Okay, so here's something you might write down for what we're doing. Just write it down by number 51. Okay, we're wanting to trap the integral, which means we want to figure out 2 numbers. One that's above the integral and one that's below the integral. That's what we mean by trap. Okay? So we want to find some number that we know is below the exact answer. Okay? Now, yeah, but we could pick some goofy number, -1,000,000, right? And +1,000,000. Have we really trapped it? I mean, that's like, hey, where's Richard today? Well, he's somewhere between San Francisco and New York. You know what I mean? You know what I mean? And we're going to talk about that with error. Yeah, I mean, we can pick ridiculously large bounds that don't really tell us much. What we want are useful bounds. We want useful error amounts, okay? So that's what we want to do on this one. So when I look at this, now we're talking about midpoint and trapezoid. So what is it that determines if midpoint and trapezoid are under? Concavity. Now this one switches concavity. So if we want to talk about under, and that depends on concavity, what do we need to find here? We got to find where it switches concavity. That's the divide and conquer strategy. Let's divide it up into pieces where we know the concavity. That's what we're doing. Now, we're going to cheat and use our calculator here a little bit, because this is why we learned all this stuff about finding inflection points, is so now when it's really useful to us, we can zip, 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 use some technology to help us when we find it. So where do we look for inflection points? Second derivative, 0. When the first derivative goes from increasing to decreasing, right? When second derivative changes from positive to negative, vice versa. When the second derivative is 0. So we're going to cheat a little bit. So we're on the scratch pad now. Go back to your, don't go to your scratch pad. Go to your, well, you can, now, when you're doing this, you got to make sure you understand when you're in your scratch pad and when you're in the area document. All we're going to do is a solve thing. We can do it on the scratch pad. So go to your calculator. We can stay in the scratch pad for this. Okay, we're going to do a solve. Or no, we need to do the second derivative first, right? Yeah, let's do the second derivative. Now, here's a quick way to do second derivative right here. You know, normally we would show our work and all that. No, we're done with the gateway test and derivatives, right? For the most part. Not promise we won't do another one. Let's do the second derivative. Did you grab that thing? What happened?
Which thing?
The second derivative one. Go to your template again. This one right here.
Oh, that one.
Second derivative. See the two? I know, we've never used it. You're right. Because I never wanted you to, because I wanted you to do the derivative. We were practicing doing derivatives, right? But now we're to the point where we know enough that we can use some of these things, and I'm not going to make you show every step on it. Second derivative. Put an x in there, and sine of x squared, right? We'll do the second derivative of this function, sine of x squared. There it is. And then we want to do what with that? Hit enter. Now we want to solve that. So let's do a solve. Okay? Equals 0. Comma x. Go outside of it. Let's do a vertical bar because we only want to look where? 0 to 2. We only care about 0 to 2. That's the vertical bar you want. Yep. Then 0 less than or equal to x less than or equal to 2, right? Probably hit Control Enter to make sure we get a decimal. I think we probably will either way. 0.8, 1.8. Looks like those are the only ones. Okay? Go back to your graph. 0.8, do a trace real quick for me. Does that look reasonable while he's doing that? It's 0.8, look about where it switches concavity. Okay? You can just type 0.8. There you go. That's real close. That's real close. That looks good. And then 1.8 down here, yeah, it kind of looks like it's switching concavity again. All right. Now, here's our divide and conquer. All right. So, from 0, and I think you should write this down with me. From 0 to 0.8, and I know I've rounded those, and then from 0.8 to 1.8, and then from 1.8 to 2 is when it switches concavity. Right? Now, the first stretch, it was what? Concave what? It was concave up. Now, which one do we know is under when it's concave up? Midpoint. So we're going to do 6 mids. We're going to do 6 mids because we know those will be under. And we're going to use our area program to do it here in a minute. Okay, now what about from 0.8 to 1.8? It switched to concave down. What do we know is under there? Trapezoid. So we'll do 6 trapezoids in there. And then from 1.8 to 2, it switched back to concave up, and so those would be 6 midpoints. Okay, now what about here? I put trapezoid in. Midpoint. What about over here? Opposite. 6 trapezoids plus 6 midpoints plus 6 trapezoids would give me... Now, on number 51, all they wanted was explain, right? We're kind of past that, right? How are we going to trap it? This is what we're doing, is trapping it, right? We know this is too little. We know this is too much. Okay, we're trapping the exact answer in between there. How do we do it? By dividing it up into its concavity sections. That's the divide and conquer strategy. Okay? All right. So now, let's do 6 midpoints from 0 to 0.8. Okay? Now, go back to your calculator and go back to your area program. So hit escape probably. Will that get you out of the scratch pad? Okay, now we're back in. Okay, now everybody, I want you to do this with us. Okay, now we're back in the area document. Now, we've got a choice here. We can do the RAM, but I don't like that. I don't like that one as well because it doesn't, I want to see more decimal places this time. And so we could go into that RAM one. I tell you what, let's do it one time so everybody gets a chance because we aborted that other one. So let's go to our RAM one. So type RAM, just type RAM and then left parenthesis. And it gives you your right parenthesis automatically. And hit enter. Notice how it turns bold. So, see, if you tried doing it on your scratch pad, nothing would happen. If you typed RAM on your scratch pad, nothing would happen, right? You've got to be inside the area document to do this. Okay? All right, so this pops up. Hit OK. So now, it says f1 of x. Now, it depends what you defined as f1 of x, and we haven't defined anything as f1 of x. So in the RAM program, we can actually type in what our function is. One of the things I actually like about the RAM program is we can literally type in what we want. So type in sine of x squared. That's our function. So type in your... Now, notice you don't get the nice pretty print when you're in here, right? Matter of fact, if you had to do an e to the x function, when you hit e, the e key on a calculator would type exp for exponential, right? I mean, so don't worry about it, but that's what you have to do in these boxes. Okay, click OK, or hit enter. Okay, now our left bound, we're going to go from 0. Now, we're going to go from 0 to 0.8, right? We're just going to do that first section where we want to do our midpoint. We're going to do 6 of them. So go 0 for the left bound. We're going to go 0.8 for our right bound. And then how many subintervals? 6, okay? And we're going to hit OK. And there is our midpoint right there, 0.165. 0.165. Okay, so hit OK. And on our paper, we'll write that down. That was 0.165. That was 6 midpoints from 0 to 0.8. All right, now, it won't do trapezoid for us. So, here's what we got to do. Steve, you guys, everybody else doesn't have to do this, but hit Control and right arrow, and let's go to another page in the document. I think it's a couple more pages over. One more. Okay, scroll down. Yeah, scroll down. Okay, there's some other little programs that are in here. RSL stands for Riemann sum left. RSM stands for Riemann sum midpoint. RSR stands for Riemann sum right. SR stands for Simpson's rule. And TRAP stands for trapezoid rule. And then this RSA2, don't worry about it. Now, these are not programs where that screen doesn't pop up and ask you to enter stuff. You just have to enter this in your calculator line. Okay? So we want to do a midpoint, we can do RSM. We want to do a trapezoid, we just do trap. And so this way you can do them one at a time. Kind of like it better because it gives you more decimal places. Okay, so go ahead and arrow back to 1.2, your calculator document. So this is all just informational stuff, and this is where the programs are stored. So if you're interested in that stuff, you can go scroll through there and look at them. But don't mess with them too much. I mean, you can, as long as you don't save it, you know, you can mess with it. Matter of fact, I would never save this when you quit out of it. I would just say don't save, and you know, then you always start with a fresh one. All right, so right here, we're going to do a midpoint. To do RSM, Riemann sum mid, okay, RSM. Notice it'll turn black when you do. Now, parentheses. Now, did you notice it said B, comma A, comma N? Now, I wish it said A, comma B, but it doesn't. It says B, comma A. So what do we want to do for that one we just did, the one that went 0 to 0.8? Well, we're going to do the 0 to 0.8 one. I just want to double check it. So you got to put 0.8, comma 0. It's backwards, okay? So if we're going to go from 0 to 0.8, we got to put 0.8, comma 0, and then comma N. What would that be? That'd be 6. We're going to do 6 sub. So this will do 6 midpoints for us. Now, go ahead and hit enter. Is that what we had? That doesn't look right. Okay, here's why. We didn't define the function. We didn't define the function. Now, for these, we have to define f1 of x. Now, again, this is where it's really critical that we're in here and not in the scratch pad. All right, we got to define it inside here. If you define it inside a document, that's different than defining it inside the scratch pad. They don't talk to each other, which is actually good. Okay, like type f1 of x right now, and we can see what function is stored in f1 of x right now. Yeah, see, that's not what we want. Okay, so what we have to do before we can do this RSM, RSL, before we can do those, we have to define the function in F1. So go ahead and do define. It's up in the document or the menu under action, or you can just type the word define. If you go to actions, the first thing is define, or you can just type it. So define F1 of x. Now everybody to use these programs is going to have to do this, because this is the only way you can do trapezoid. The RAM program doesn't have trapezoid in it. So if we get to the next quiz and I ask you to do T50, you've got to know how to do this, okay? I'll say define f1 of x to be our function, sine of x squared. Hit enter. Now do RSM. You can just go up and grab it if you want. RSM, because this is just a regular calculator page, works the same way. Hit enter. Bingo. Isn't that what? Oh. What do we have?
Up above 1.65.
Oh yeah, because it rounded. See, and that's why I like having more decimal places. Okay? I like having more decimal places. All right. So, now back to where we were here. All right, so we had 0.165, so that wasn't bad. Okay, so now we can quickly do these. So let's do trap. Let's do trap, and then this one we want to go from 0.8 to 1.8. So remember, we've got to write those backwards. So trap 1.8, comma 0.8, and then 6. .716. Okay, then do the next one. We want to do a mid for this one. We do a mid now. We want to do a mid from 1.8 to 2. So you got to go 2, comma 1.8. That just messes me up all the time. I always type those Wrong. Okay, negative. That makes sense because it went below, so it should be negative. 0.0887 or 0.089, negative. Okay, now go and do them the reverse. Now do a trapezoid. Okay, now somebody else, while he's doing that, somebody add these three up for me. Okay, let's get these three added up here. Now, to be honest, these aren't going to be that much different because we're doing midpoints and trapezoids are fairly accurate, and so these probably aren't going to be a whole lot different. 0.792. All right. How's he doing? 0.168. He's got. What was the next one? 0.733. They're off a little bit. And these are all a little bigger than the ones over here, right? Which we would hope they would be. And then what was this last one, Steve? So about the same. Okay? So now let's add those three up. Okay, now wouldn't it be fairly convincing that our exact answer is somewhere between them? Right? Now, again, you might legitimately be saying, geez, that was a lot of work for, you know what I mean? Well, partly this is just the theory of it, to see what we did, why it worked, and then to understand where we're headed with this is how does a calculator know, and Steve did this earlier, go back to your scratch pad, Steve, when Steve did this on his scratch pads for us, and he got, scroll back up where you did the integral for us, okay, you had 0.804, right, 0.804, and I think that is between, 0.804 is in between these two, right, and how does a calculator know that it's accurate to however many decimal places? Well, it has to do with what's under, what's over, and how much under and over is it, what causes it to be under and over, concavity and those kind of things. That's all going to play a role in how the calculator is programmed to do that. Now, we love it that we can just type this in like Steve did. We love the fact that we can just type this into our calculator and have it spit out this answer, but there's a lot going on behind the scenes, right? And one of the reasons you signed up for AP Calculus was to investigate that. You didn't know it at the time, but that was what you were doing. Okay. All right. So we're gonna get right after it here. We're gonna get started on homework because there's not a lot more to tell you. Really, the new thing, we're just gonna stay in this section 6.1. The new thing is this document I gave you and being able to use it, be able to make it work. Okay. So your second line here, your second line on 6.1. All right. Now, what I want you to do, it starts with problem number 5. Now, some of these are going to be things you have to do a few calculations. Remember, if it's 10 or more subdivisions, you automatically go to the calculator. Automatically. All right, so here's what I want to do. I want to kind of work 5 together, and then I'll let you move on and keep working. All right? So, let's take a look at what number 5 says. Okay, we got I is equal to the integral from 0 to 2 e to the x squared dx. Now, that is another function that we cannot do the antiderivative. Right? So we can't find an exact answer other than to go to our calculator and have it give us an exact answer. But even that, as we've discovered here, is not an exact answer. Your calculator behind the scenes is doing an approximation technique. But what it's doing is giving us an answer that's exact out to however many decimal places it's showing. All right? So in part A, they want you to do L10, R10. Well, as soon as you read a 10 there, T10, M10, and S20, as soon as you see those double-digit intervals, you have automatic permission to use this area document right here. Now you want to do it with the RSM, the TRAP, the RSL. Okay, remember what those were now. A left is RSL, B, comma, A, comma, N. RSM is midpoint. RSR is right. TRAP is, of course, a trapezoid. and Simpson's rule is that. Okay, that'll give you all of them right there. Okay, that'll give you all 5 of them. Or you can do that RAM one, but then you'll have to do the trapezoid on your own. Okay? All right, so I'm going to let you go do those 5 real quick here on your calculator. And then we're going to talk about B and C together. Part B together, and then I'll let you do part C. All right. Take a few minutes here to get that, and then if you're having trouble, ask somebody or ask me. Okay. You've got to be able to use that area document, either the RAM or these other programs. Preferably be able to use both. Again, remember, if you're using the RSL, RSM, you have to define F1 of X. Okay? If you're using one of those, RSL, RSM, RSR, TRAP, or SR, you have to define, in the area document, you have to define F1 of X to equal e to the X squared. Okay? Otherwise, you're not going to be getting the right number. Okay, what are you getting for, has anybody done trapezoid? Because that one you have to use that one for. 17.170, and did you define it to be that e to the x squared? That number sounds right. So if you're not getting that when you do the trap, you didn't define the f1 of x to equal e to the x squared. And it has to be f1 of x, not f of x. Okay, because the program that is doing that calculation is using f1 of x, so you have to define it. If you run the RAM thing, and once you define it, it's defined in the area document. It'll stay that until you redefine it as something else. So if you go on to a new problem, you define it again, and then that'll replace the definition from before. Okay, what are we getting for L10? R10? 530. M10? And S20. Is that right? Now when you do Simpson with 20, if you're doing the RAM program, you got to run it again because it's 20 subdivisions, not 10, right? Did you do that, or did you do this over here?
I did. Well, I had SR and then the parentheses 2.
Okay, and that should be right. And so that's what?
16.45.
But so a few people in the other class did the RAM one, which tells you left, right, midpoint, and Simpson, right? Problem is, if you run the RAM one and tell it 10 subdivisions, that'll give you L10, R10, and M10. But that's giving you S10, right? Not S20. So you have to rerun the RAM program to do S20. Okay, just so everybody's clear on that. But what Steve did is foolproof. SR parentheses 2, 0, 20. That gives you S20. Okay? All right. a few people in the other class were confused because they said, well, wait a minute, didn't we have that formula where it was half, like if you do S of 2n? That's only if you're using this formula, right? Only if you're using this formula is that true. Okay, that's when that would come into play. But if you're doing an S20 and you're using these programs, your number of subintervals is 20. Okay, that's what it needs to be. All right, now, here's part B. Okay. Steve, read me part B.
I was going off the board.
Okay, somebody who's got it. No, that's fine. Mandy, read me part B.
Use L10 and R10 to find a bound on the approximation error made by T10.
Okay. Use L10 and R10 to find a bound on the approximation error made by T10. Okay, well, first of all, would you agree that this is the approximation error made by T10 right there? Right? That's what that is, the approximation error made by T10. Now, we can't calculate this like we did on today's homework because we don't know what I is, right? We don't know the exact area. So now what we're looking for is a bound on that area. It says find a bound for the computational area or the approximation area made by T10. In other words, that's like asking for the max error. That's what that's saying. What's the most? That's what it means by a bound. What's the most that T10 is off? Right? We don't know how much it's off. But I think we could decide what's the most it could be off. Here's why. And they said use L10 and R10. Okay, so here's L10 and here's R10. What can you tell me about those? Okay, one thing we know is the average of those is T10.
So you could take
So one of these is too little and one is too much. So here's what I'd like to see on your paper. Let's make a range here. So L10 is over here. And that's 11.810. And R10 we know is over here, and that's 22.530. So I'd like to see you have that kind of on your paper here for part B. Now, what do we know about the exact answer? It's somewhere in there. Now, do we know that it's probably closer to the middle? Yeah, I suppose. But essentially, what do we know for sure? We know it's in there somewhere. We know the exact answer is in there somewhere. Now, Steve, tell me again what you told me about T10.
it's the average.
So where is it? Where is T10 in this? Isn't it exactly in the middle? Now, that's only true because we know T10 is the average of L10 and R10, right? We don't know on part C, when you get to part C, that it's exactly in the middle. But because we know T10's in the middle, let's go ahead and put it there. So we know T10 is exactly in the middle, and that's 17.170. We know the actual answer, well, yeah, but we're not even talking about M right now. We know the actual answer is in here somewhere. But you're right. I mean, we could put M in here now, and then we could know it's in. Okay, but they didn't even want us to use M. They just said use L and R. So we know the actual answer is in here somewhere. So what's the most that T10 could be off? Yeah, and has anybody subtracted those yet? Subtract those. In other words, the most it could be off is if I was way over here. Now, we don't think it is, right? But if the actual answer was way over here, what's the most it's off? 5.36. So it's 5.36 this way and 5.36 this way. So really the best answer for this question is find the bound on the error. What's the most that T10 can be off? 5.36. Now, somebody got the back marked. If you look up 5B in the back, it says 10.72. Okay? It's the whole interval, right? Now, why did they say that? I like our answer better, 5.36. But let's talk about, let's forget what Steve said. Steve told us the trapezoid's exactly in the middle. Let's pretend we didn't know that. Let's pretend that we knew this was under, we knew this was over, and we knew that T was in there somewhere, right? What's the,
so if you
then you, yeah, because let's say T was way over here,
yeah.
and the actual answer is way over here, right? Then they'd be off almost the whole interval, right? So the most they could be off is the whole interval, 10.72. So isn't that true? I mean, if right, I mean, see, bounds are tricky things. For example, I will tell you right now that the bound on the amount of money I have in my pocket is $10 million. That's the upper bound of how much money I have in my pocket. Right? Actually, 100 million is an upper bound on the amount of money I have in my pocket. Right? Now, how useful are those in telling you how much money I have in my pocket? Not very useful, right? They're not very useful. Okay, now if I said $7 is an upper bound on how much money I have in my pocket, then that's more useful. You have a pretty good idea, right, of what I have in my pocket. So when we talk about that the most this could be off is 10.72, we know it's off less than that, right? We know it's better than that. So it's not as useful. So I like our 5.36. It's more exact. Now when you go to part C, and I'll get to you guys a second. When we get to part C, they're going to say use M and T to talk about S. Well, again, we don't know S is right in the middle of M and T. We know it's in between there somewhere. That's fine. I'll get it a second. So we got M and T. We know S is in there somewhere, so that's what's going to happen to C. So you guys do C. Okay, what was the question, Ryan?
Oh, it's irrelevant now.
Oh, Sam?
Don't worry about it.
Oh, sure. Yeah, if I'd known it was Lane, I definitely would have. Well, you were knocking, they all wanted to come in. I said, "Well, I didn't wait." Were you? Okay.
I'm just gonna say.
Yes.
Can it be exactly 5.36, or is it just a little bit underneath that? Like
Wouldn't it be less?
Well, right, because we know that this isn't exact. Neither one of these exact. So we know that I isn't exactly there. But again, we're saying upper bound. I mean, so any number above what the actual error is the max error, right? So you're right. Is it possible that the actual amount of error is probably a little less? See, because remember, we're not saying it's off by 5.36. We're saying that's the most it can be off. That's what we're saying.
So wouldn't it be less than instead of less than?
Instead of less than or equal to, I suppose you could say. I suppose you could say, but it's not wrong to say less than or equal. You know what I mean? It's not wrong to put the equal. It's like, see, my algebra 1A, 1B kids have a tough time with this. When I put 10 is less than or equal to 16, that drives them nuts. Is that true?
Yeah.
That 10 is less than or equal to 16?
Yeah.
Yeah. They say, well, no, it's not equal. It's less than. It should just be 10 is less than 16. Well, yeah, that's true, but that's true also, right? Because it's or. It could be one or the other. See, so that's kind of the same thing there. Could we just put less than? Yeah, but it's not wrong to say less than or equal. So we do it. Okay, you guys go ahead and finish 5C, and then just keep right on working with the rest of it. Got the rest of the time to work on that.